Translation of DNA to protein is one of the most important functions of SnapGene. Our software supports two types of translations: full sequence translations and feature translations. Let's start with full sequence translations. I downloaded this sequence from the Saccharomyces genome database. It encodes the Sec13 gene plus 1 kilobase of flanking DNA on either side of the open reading frame. To find the Sec13 gene, I press the Show Translations button in the side toolbar. Top strand ORFs show up as orange and bottom strand ORFs as green. Here's Sec13 in the middle. Notice that there's another top strand ORF on the left and a bottom strand ORF on the right. If I switch to sequence view, I see that the top strand ORF doesn't have a start codon. That's because the default behavior is to allow ORFs to begin at DNA ends, as indicated by this yellow message. If I want to change that behavior, I can use the translation options command. The default is to require a start codon except at DNA ends. If I uncheck except at DNA ends, the ORF will be forced to begin at a methionine codon. Notice that it's also possible to change other parameters, such as the minimum length of an ORF. I'll press Cancel to stick with the normal behavior. By default, the Show Translations control only displays ORFs, but I can use this pull-down menu to see other options. For example, if I choose all 6 frames, the entire DNA sequence is translated in all 6 reading frames. In many cases, showing this type of full sequence translation, or even all of the ORFs, is more information than I need. For most purposes, the best way to work with translations in SnapGene is to use translated features. Let's see how that works. I'll switch back to Map View and click on the Sec13 ORF to select it. Now in the Features menu, I'll choose Add Translated Feature. I'm typing the name as Sec13. Note that SnapGene has already marked the feature as being a coding sequence, or CDS, meaning that it's translated. So all I need to do is press OK. A feature called Sec13 has been created, and I can turn off Show Translations so that only this feature is visible. Now if I switch back to Sequence View, the translation is displayed above the feature. I can switch back and forth between 1- and 3-letter amino acid codes using this button in the side toolbar. Sec13 is simple because this gene has no introns. Let's take a look at a gene with an intron. This gene is called SAR1, and I downloaded just the open reading frame with no flanking DNA. But the Show Translations button doesn't display a complete ORF because of the intron. I'll switch to Sequence View and choose the Frame plus 1 only option for showing translations. Now we see the start codon, but there are a bunch of stop codons because of the intron. I'll go ahead anyway and define a feature called SAR1. First, I'll select the entire sequence using the Select All command in the Edit menu, and then I'll create a translated feature using the Add Feature command. I'm naming this feature SAR1, and this time I need to check the checkbox to ensure that it's translated. Now the SAR1 feature is visible, and as expected, it's full of stop codons. I'll turn off Show Translations to simplify the display. I want to annotate the intron in this gene. According to the Saccharomyces genome database, the intron lies between bases 29 and 167, so I'll select those bases using the Select Range command in the Edit menu. To create the intron, I go to the Features menu and choose Delete Feature Segment. The Edit Feature window appears. I press OK, and the intron has been created. The translation is updated correctly, even though the intron splits the codon for phenylalanine 10. I can retrieve the amino acid sequence of SAR1 by using the Copy Translation command in the main toolbar. If I switch to a text window, that translated sequence can be pasted. Finally, let's switch to another file to see a couple of neat tricks with translated features. You'll notice that this fragment of Sec 7 lacks a stop codon, so the translation continues beyond the end of the feature. Then the run-on translation links up with the next translated feature, which is monomeric EGFP labeled MEGFP. These two features are in frame. What if they weren't in frame? To see how that would look, I'll insert a single base just before the MEGFP feature. Now the Sec 7 translation runs on past the MEGFP feature. In other words, SnapGene lets you see at a glance whether two features are in frame. I'll press undo to erase that change. This version of EGFP is monomeric because it has an alanine to lysine mutation at position 206. But if I scroll down, I see lysine at position 207 instead. The reason is that EGFP contains an extra valine inserted just after the start codon. I'd like to edit MEGFP so that it follows the convention for numbering of GFP. In other words, I want the numbering to skip this extra valine codon. I'll choose Create Feature Segment from the Features menu. I'm naming that segment 1A because it's valine 1A. Now I'll click the Options button. Segment 2, consisting of valine 1A, is automatically selected. I'll click here so that the numbering skips over segment 2. I want segment 3, which is the rest of MEGFP, to start at amino acid number 2, so I'll choose 3 from the segment menu and then press this button so that segment 3 starts at +2 instead of +3. Now if I hit OK twice and click in the window to deselect, I see that the numbering skips over valine 1A. And if I scroll down, that lysine is number 206, as it should be. With these powerful yet simple tools, SnapGene makes it easy to work with translations.